Good morning and welcome to this next lecture on vibrations of plates and shells. We had finally arrived at the equations of motion, and I had just written the first equation of motion. So here are the rest, and as I said, maybe this first and last time I will write them together because it is quite cumbersome. So the second equation is minus del alpha 1 n1 2a2 minus del alpha 2 n2 2a1 minus n21 del a2 by del alpha 1 plus n11 del a1 by del alpha 2 minus a1 a2 q23 by r2 plus a1 a2 rho hu2 double dot is equal to a1 a2 q2. So this was in the alpha 1 direction, this is in the alpha 2 direction, okay. And the next one minus del alpha 1 q13 a2 minus del alpha 2 q23 a1 plus a1 a2 n11 by r1 plus n22 by r2 plus a1 a2 rho hu3 double dot, that is equal to a1 a2 q3. So this is the alpha 3 equation of motion, alpha 2, this is in the alpha 3 direction. The other two are moment equations, and they end up as equilibrium equations because we have ignored rotational inertia. So the last two, so let us see, this is 1, this is 2, this is 3. So the fourth one is del alpha 1 m11 a1 plus del alpha 2 m21 a1 plus m12 del a1 by del alpha 2 minus m22 del a2 by del alpha 1 minus q13 a1 a2 equal to 0. It's an equilibrium equation, okay. Then del alpha 1 m12 a2 plus del alpha 2 m22 a1 plus m21 del a2 by del alpha 1 minus m11 del a1 by del alpha 2 minus q23 a1 a2 equal to 0. This is the fifth. So those are the other 5 equations, okay. So the first objective is achieved. So we have a general set of equations. So if you substitute the right A1, A2, R1, R2, then you will get the appropriate equations. Okay. So if you substitute A1 is equal to 1, A2 is equal to 1, R1 is equal to 1, R2 is equal to 1. I'm sorry, big mistake. Inertia, R1 is equal to infinity and R2 is equal to infinity. Okay. Then you will see that this equation becomes the equation for a flat plate, a flat rectangular plate. Okay. So and this one will look like an equation for axial waves in a rod. Or longitudinal waves in a rod. Okay. So we have the general set of equations now, and they are called Love's equations. And the beta definition has to be used in here. Beta definitions, beta 1, beta 2 definition, to make epsilon 1 3 and epsilon 2 3 equal to 0 has to be used in here. Okay. Now we have to focus on the boundary conditions. All these equations put together, they form an 8th order PDE in space. Okay. And so at a given edge, this is my alpha 1, this is my alpha 2, at a given edge, at a given alpha 1 edge, or at a given second alpha 1 edge, there can be at most 4 boundary conditions. 4 boundary conditions. Okay. But if you look at the boundary term, there is a boundary term at alpha 2 constant edge, or let us say alpha 1 constant edge. Okay. You have 1, 2, 3, 4 and 5 terms. You have 5 terms. Okay. So there is some kind of a incompatibility, and this was first observed by Kirchhoff. Okay. So he made a change. Okay. So what did he do? So just for once if you have, let's say this is alpha 1, okay, and this is alpha 2, alpha 1 and alpha 2, okay. So you will have N22 here, okay, then you will have N21 this way. This is an alpha 2 constant edge, okay. this is at an alpha 2 constant edge. Then you will have, let me draw Q23, then this is alpha 3 direction, let's say, then we will have, this will be M22, okay, and M21 on the face, M21, the moment due to shear. So now this is the alpha 2 constant edge, okay. Similarly, if I just reproduce that edge over here, okay, this is alpha 1 and this is alpha 2, okay. So M22 will be associated with this out of plane beta 2, okay. Then N22 is associated with U2, okay. Then N21 is associated with U1, okay. Then Q23 is associated with U3, okay. Then M21, this M21 is associated with the in plane beta 1 here, okay. Beta 2 moves out of the plane or out of this surface, beta 1 is in the surface, okay. So now if we look at this boundary term, integral alpha 1 at a alpha 2 constant edge, we have N22 star minus N22 delta U2 plus N21 star minus N21 delta U1 plus Q23 star minus Q23 delta U3 plus M22 star minus M22 delta beta 2 plus M21 star minus M21 delta U1 by R1 minus 1 by A1 del alpha 1 delta U3, okay, A1 d alpha 1 dt, okay. So why? Because beta 1 is U1 by R1 minus 1 by A1 del alpha 1 U3. So the delta of beta 1, okay, this used to be delta of beta 1, variation on beta 1. So now beta 1 has been opened out. Why? With this combination we get 4 boundary terms. We will see what happens, okay. So now what happens is, the moment you open out, this term has a derivative on the variation. So integral t1 to t2 integral over alpha 1 m21 star minus m21 del alpha 1 delta u3 d alpha 1 dt. This now can be written as, okay, t1 to t2 m21 star minus m21 delta u3 dt, okay, end points of alpha 1 minus integral t1 to t2 integral alpha 1 del alpha 1 m21 star minus m21 d alpha 1 delta u3 dt. Okay, so this is a term right at the corner, actually it's a corner, okay, and this term will be 0. Based on the conditions at the boundary, this term will be 0, okay. So now what do? We have broken this up into two pieces. So if we recombine integral alpha 1 n22 star minus n22 delta u2 plus, here comes the combination, n21 star plus m21 star by r1 minus n21 plus m21 by r1 delta u1 plus m22 star minus m22 delta beta 2 plus q23 star plus 1 by a1 del m21 star by del alpha 1 minus q23 plus 1 by a1 del m21 by del alpha 1 delta u3, close the bracket, a1 d alpha 1 dt. Okay. Similarly, the second line integral gives you integral t1 to t2 integral alpha 2 n11 star minus n11 delta u1 plus n12 star plus m12 star by r2 minus n12 plus m12 by r2 delta u2 plus m11 star minus m11 delta beta 1 q13 star plus 1 by a2 del m12 star by del alpha 2 minus q13 plus 1 by a2 del m12 by del alpha 2 delta u3 a2 d alpha 2 dt. So now we have 4 boundary conditions. We have done a combination and we have 4 boundary conditions. Okay. At this point it may not, it's purely mathematical, it doesn't have any physical basis, but I'll give you a physical basis in a few classes. Okay. So now these have been renamed. This is given the name T21, this is given the name V23, this one is given the name T12, and this, the last one lower, is given the name V13. Okay, or just this term, actually just these terms, these terms one side. Okay, so what are they? So they are the V13 is given by Q13 plus 1 by A2 del M12 by del alpha 2. V23 is given by Q23 plus 1 by A1 del M21 by del alpha 1. Okay, so these are now named as Kirchhoff effective shear stress resultants of the first kind. Then T12 given by N12 plus M12 by R2, T21 is equal to N21 plus M21 by R1. These are called as the Kirchhoff effective shear stress resultants of the second kind. Okay. So as a result, the boundary terms look like T1 to T2 alpha 1 N22 star minus N22 delta U2 plus T21 star minus T21 delta u1 plus m22 star minus m22 delta beta 2 plus v23 star minus v23 delta u3 a1 d alpha 1 dt. Okay. So, this term by itself must be 0. Okay. Similarly, integral t1 to t2 integral alpha 2 n11 star minus n11 delta u1 plus t12 star minus t12 delta u2 plus m11 star minus m11 delta beta 1 plus v13 star minus v13 delta u3 a2 d alpha 2 dt must be 0. Okay. Further, these are kinematic terms that are allowed to vary in any manner. These are variations that are allowed to vary in any manner. They are completely independent variations. So, each of these terms has to be 0. Each of these terms has to be 0 in order for the total to be 0. Okay. So, I will make some comments later. Let's complete this part. Okay. So, these are at the alpha 2 constant edges, these are at the alpha 1 constant edges. Okay. So, this gives us the boundary conditions. Okay. The Hamilton's law affords us the boundary conditions in addition to the differential equations. So, we have the boundary condition alpha 1 constant edge. Okay. Because each of these variations is independent, therefore, this term total term independently has to be 0 in order for the total to be 0. Okay. So, at an alpha 1 constant edge, so we have alpha 1 and this is the alpha 1 constant edge. So, what do we have? We have okay, alpha 1 constant edge. So, we have n11. So, in order for this term to be 0, in order for this term to be 0, the n11 from within the material should be equal to n11 star what is applied exterior to the structure, or delta u1 is 0, that means u1 is specified. Okay. Similarly, from here m11 from within the structure is equal to what is applied exterior, or beta 1 is specified. That is why delta beta 1 is 0. Okay. Similarly, V13, okay, first kind shear is equal to what is applied exterior, or U3 is specified. Similarly, T12 is what is applied exterior the structure, or U2 is specified. Okay. In the most common systems, you don't have a force specified as a non-zero value, that is rare. Okay. So what you will have is a free surface. So what will happen is, at a free surface the exterior is 0, what is applied exterior is 0, so the boundary condition will be N11 is 0. Okay. Similarly, at a free surface, okay, exterior M11 moment is 0, and therefore the boundary condition is M11 is 0. Okay. Or it is held, it is fixed in some manner, so that U1 is 0, or it is fixed in a manner that the slope is 0 and therefore beta 1 is 0, or it is supported in a manner that U3 is 0, and so forth. Okay. Similarly, at an alpha 2 constant edge, this is the alpha 2 constant edge, you will have N22 shall be equal to N22 star, or U2 is specified. Okay. Once it is specified, delta U2 is a 0, it can be changed. Okay. Similarly, M22 is equal to M22 star, the external applied moment, or, so these are or actually. Okay. So or you have beta 2 specified such that delta beta 2 is a 0. Similarly, the first kind shear is equal to what is applied exterior, or U3 is specified. And lastly, T21 is equal to T21 star, or U1 is specified. Okay. So time is run out, so I will end the lecture here and we will continue from here in the next class. Thank you.